Hi, in this lecture I'm going to talk about norms, which is basically how we measure the magnitude of a vector or a matrix. This goes with chapter 2.5 in the Deep Learning textbook, so I encourage you to read that after watching this lecture. This is a slightly easier topic to cover than something like linear independence and span, so this will be a nice little break. But it's still, let's still start with something that's a little simpler than norms. So I mentioned just a couple seconds ago that the norm is how we measure the magnitude of a vector or a matrix, but let's start with scalars. How do we measure the magnitude of a scalar? Well, you might already know the answer already. You take the absolute value is the answer. So if we say you have a number 50 and a number -50, if you have a number line, you can think about these numbers still being the same distance away from 0. It's -50. So having the same distance away from 0, thus having the same magnitude, but one's in one direction and one's in another direction. So the way we just kind of distill this to just the magnitude is we take the absolute value of them, and these both return 50. So we get the magnitude of our scalar number by taking the absolute value. So the kind of vector component, the vector version of this, well, let's start with an example, I guess, right? So how do we kind of find out what the vector version of absolute value is? Well, let's take a specific example. So say we have some vector like this. Let's make this a dotted line. So this is some vector 2, 1. So let's have this length be 2 and 1, and this is the origin right here. You can imagine a Cartesian plane if you would like. But this is going to be 2 and this is 1. Right? So how do we measure the magnitude of this vector? So vectors both have magnitude and direction. If you watch Despicable Me, vectors both have magnitude and direction. But we don't really care about the direction. Right? So if we had two vectors like this, and these were of the same magnitude, we wanted that if we take the norm of this vector and we take the norm of this vector, even though that they're in different directions, we still get the exact same value because they're the same length. But what can do that? Well, think about it for a second. So this one here, this is some 2, -1, right? But we want something that takes this 2, -1 and this 2, 1 and returns the same value. Well, you might remember in geometry from the Pythagorean theorem that this might give us the answer. If we have 2 and 1 here, 2 and 1 here, we can use the Pythagorean theorem to find the length of this vector. And the length of this vector is essentially the magnitude, right? The length of a vector is its magnitude. It's just its direction that changes. But the length of a vector is its magnitude. So getting the magnitude of this vector would be as simple as using the Pythagorean theorem on the 1 here and the 2 here. So let's do that. So we take this, so we do 1 squared plus 2 squared, and let's represent this magnitude as x equals x squared. So this becomes x equals 1 squared is 1, 2 squared is 4, so this x squared equals 5, so then x equals square root of 5. So the length and the magnitude of this vector is square root of 5. Similarly, if we took this vector, we would end up with the same thing, because we would get -1 squared plus 2 squared equals x squared. And since this negative is inside the square, that becomes the same thing as 1, and we still get that x is equal to square root of 5. So this is also square root of 5. So this is a norm. It gives us the magnitude of a vector, but disregards its direction. So how can we generalize this to something of a vector of maybe 3 dimensions, or 4 dimensions, or n dimensions? How can we take the norm of an n-dimensional matrix? And no longer we can kind of imagine this Pythagorean theorem thing, because we are only familiar with Pythagorean theorem in 2 dimensions. But I'm going to see if I can make it clear that we can actually extend this Pythagorean theorem idea into multiple dimensions and still get a good formula for the norm. So generally, in 2 dimensions, if we have some vector x and y, that means we have a height of y and a length of x, and that means we can find this value here, this magnitude of the vector x, y, by basically doing the Pythagorean theorem or the distance formula. And now we have 2 x's, that's kind of, so let's call this the magnitude m. So we have some x and y, and we have some m. And generally, in 2 dimensions, as we just demonstrated, that we can find m by taking x squared plus y squared and then squaring it, right? So essentially just the Pythagorean theorem. So m equals that, right? It's a right triangle. But what if we have some z? If we have some z, So I'm going to prove to you, in a way, that we can just add on to this. And that's going to be the norm of this new three-dimensional vector. But let's see why that's true. So let's go into 3 dimensions now. All right. So I'm trying to, just to keep it over here, I'm trying to show that the norm of a 3-dimensional vector, oopsies, equals x squared plus y squared plus z squared. So we're going to see if we can just, if this is true, if we can find the magnitude of a 3-dimensional vector kind of in the general form using this kind of extension of the 2-dimensional sort. So let's draw our coordinate axes. All right, that's our 3-dimensional coordinate axes. And let's, in some nice color, maybe blue, draw our vector. So that's going to be our 3-dimensional vector. So this vector exists in x, y, and z space, so this is going to be some x, y, z vector. Maybe I should do that in blue. All right, so that's our x, y, z vector. So if we go from the tip of this point here, and you can imagine this is kind of jutting out, in all 3 dimensions. If we kind of take this tip here and we draw a line directly from this to the xy plane, we might get some point right there. Right, so this point here, if we kind of imagine over here what the xy plane looks like, and let's kind of, so this is x, this is y, and this is z. If this is the x plane and this is the y, you can imagine this point kind of dropping down somewhere here, right? So somewhere here. So now let's draw some line in this xy plane going from the origin to that point here. So that's kind of drawing this line here. Right? So let's draw that line from here to there. Now we can actually measure now this is some diagonal in 2D space, so we can measure the direction from the x-axis and the direction from the y-axis. So we can say some direction in the x-axis here and some direction in the y-axis. So how far is this kind of diagonal line in the xy plane from the x and y axes? So this vector has the kind of coordinates x, y, and z. So first let's see if we can find the length of this, right? This is kind of a geometry problem. We want to find the length of this, and we're going to show that the length of this is equivalent to this, right? Because the length is the same thing as the magnitude. So let's just kind of piece together using a few different Pythagorean theorems and see if we can prove that. So these are all right angles here, right? So this is a right angle here, that's a right angle there, and this is a right angle here. Right, so first let's consider this triangle here, or this triangle here, right? So this triangle here, let's try to find this diagonal here along the xy plane, and then we can use that in the Pythagorean theorem to figure out this later. Right, so let's find the length of this thing in the xy plane first. So that's simply going to be our 2D example, right? That's going to be x squared plus y squared equals, let's call this k, the magnitude of this line here, k. Right, so that's simply going to be x squared plus y squared equals k squared, so that means we're going to get k is equal to square root of x squared plus y squared. So the length of this is going to be square root x squared plus y squared, as we just talked about, right? So that's going to be the length of this. So that's all fine and dandy. But we're actually trying to find this. But now that we have this diagonal here, now we just have to add this thing here, and then we can do another Pythagorean theorem to find the length of this blue line. So we know that the length of this k here is this. So what we're doing now is this height here, which is z, we're doing k squared plus z squared equals our magnitude m. But we know that k squared is square root of x squared plus y squared, so we can replace that. Sorry, like that. Right, so we can get rid of this, so that gets rid of the square root, so we get x squared plus y squared plus z squared equals m squared. And then we'll see, and you can probably see it coming already, if we square root this other side, we get m equals square root of x squared plus y squared plus z squared. So you can see that the magnitude of this thing in 3 dimensions follows the exact same pattern. So we can kind of make the safe assumption that in 4 dimensions, which I won't try to draw because I don't even know how I would begin to try to do that. In 4 dimensions, if we had some 4-dimensional vector x, y, z, and say k, then the magnitude, or the norm of that vector, would be x squared plus y squared plus z squared plus k squared. So generally, the formula for this norm, and we're going to realize this norm is just one of many, many, many possible norms you can use. But this maybe is one of the most famous, and I'll give the name of it in a second. We can kind of show a kind of general formula for this would be if we have some vector like this, x, let's say, and we index these x1, x2, x2, x3, all the way to xn, then we can say the norm in the way that this kind of Pythagorean theorem-esque norm is the sum over I until n of each of the index, so xi squared, and square rooted. So or you can, it's the same thing as saying this, but we'll just represent it with that little nicer fractional power. So the norm that we just talked about, and I'm tired of just calling it the norm, the name of this is the Euclidean norm, because it measures the Euclidean distance of the vector. The Euclidean norm, this is the formula for the Euclidean norm for some vector x. So basically you cycle through, you go for this first element here, and then you square it, and then you add it to the second element, you square it, and then once you have this final sum, you just take the square root of it. And you'll see that's the exact same thing. Say if we have a three-dimensional x, y, z. Basically, we can calculate this as xi is going to be x, right? So this is going to equal, and in this case when we have three variables, this is going to be, our first one is going to be x, so we're going to get x squared, and then we're going to go to our next one, so plus y squared, and then plus z squared, and then we'll take the square root of it, just like we did with the Pythagorean theorem one, and you can see they're equivalent. So this just extends it to any n-dimensional vector, and this is the Euclidean norm. But the one interesting thing here is this is just a part of a larger family of norms called the LP norms. And the formula for the LP norm is generally, so this is just kind of saying the LP norm of x, is the sum over n and I, so that's the same thing. So the sum over every element in the vector to p, and doing 1 over p now. So you can see that the Euclidean norm is just a special case of this LP norm when p equals 2. So you can get an infinite amount in this kind of LP norm family, and this is just one example of one of the things in the LP norm family. But all of these satisfy the conditions of being a norm. And these aren't super important to consider, but the conditions of a norm to be defined formally as a norm are the following. There's three conditions for something to be considered a norm. If a norm function doesn't obey these three conditions, it's not a norm. The first one is pretty simple. So if we represent the norm as f, the function f, if we say the vector function f is the norm, then f of x has to equal 0 when x equals 0. So when x is the 0 vector, so when x is something which is like this. So it's all zeros. So when x is the 0 vector, the norm of x has to also be 0. Secondly, it has to obey the triangle inequality. And this makes, the reasons for this are a bit complex, but it basically makes things consistent further down the line when people are trying to do proofs with these things. So specifically, f of x plus y has to be less than or equal to f of x plus f of y. And lastly, for any constant alpha, so what this upside down a means just simply means for any alpha, where alpha is a real number. So this is a very technical looking thing, but we're basically saying for some constant alpha, for any constant alpha where alpha is a part of the real number set, then the norm of the vector times the vector times the constant is equal to the function, the norm of the vector times the constant on the outside. So you're basically saying that when you multiply this vector by the constant, and then take the norm of that, it's the same thing as taking the norm of the vector and then multiplying that norm by the constant. So these are the three conditions of a norm to be a norm. And you can see for yourself, I won't do it here, but the LP norm satisfies this. So I just have a couple more important norms to talk about, and that's when p equals 1. So that's called the L1 norm. So let's look at that case specifically. So when the L1 norm exists, basically what we're doing is we're saying that so the L1 norm is as follows. Oh, and one thing that I now forgot to put this in the form for this is we take the absolute value first, and this makes this make a lot more sense. So we some I, some n. So you notice that this is the L1 norm, so this just cancels out to become this, and it just becomes that you're summing over the absolute values of each element in the vector. So that's another often used norm in machine learning. The last one is a matrix norm, and it's when you're trying to calculate the norm of a matrix, which is done a lot less, but it's good to know. And the important one that's used, that's actually barely used outside of machine learning, is called the Frobenius norm. And basically it's the LP norm for matrices. So if you have some matrix A11, A12, all the way to A1, n, and then you have this going down the other direction, 2, 1, A2, 2, A2, and then you have this going on until AM1, AM2, to AMN. If you had something like that, if you had a matrix like this, the LP norm, the Frobenius norm, would basically just be doing this, but instead of summing over all the elements in the vector, you sum over all the elements in the entire matrix. So basically you're going to be doing, for the Frobenius norm, is you're going to be adding A11 and then squaring it, plus A12 and then squaring it, and then going all the way until here, and then going to this next level and then doing this and then squaring that, plus this and squaring that, and then taking the square root over all of those. So it's basically squaring and adding each of the terms and then taking the square root of it. The official kind of formula for this, if you want it, although it's not really that helpful if you just understand what it is summation over all the I and j until, I guess, mn. And then you're taking the aij, squaring it, and then you're taking the square root of that. So that's the Frobenius norm. So that's for matrices, and it's generally the only one we use in machine learning for matrices. And then finally, just here, this is the L1 norm. And then I erased it, but the one that was before was the Euclidean or LP norm. And those three are the most frequently seen ones you're going to be seeing in machine learning and during this course. So just important to know. And again, those are those three conditions that norms have to satisfy. Okay, that about covers it. See you next lecture.